Hi, I'm Sylvain FOURNIER and I come from MATEIS Laboratory in Lyon, and I'm glad to present you my project, which is a PhD project about additive manufacturing by stereolithography for tough ceramics that will be applied for medical applications. So the outline of this presentation will be first to explain you what I do and why I do it, the aim of the project, and why I have chosen stereolithography as the technique to print biomedical ceramics. And after, I will present all the scientific and the technological challenges that are involved by this technique. So first, what do I want to do is to print ceramic prosthesis with a tailored geometry to adapt to each patient's specificities, to the lack of material that exists in the skeleton. So for this, 3D printing, additive manufacturing is a good solution. And we managed by stereolithography to make some good results, good shapes with scanned images. We also want to improve osseointegration, so the bone regrowth and the bone adhesion, the cell proliferation on the materials we bring. And also we need mechanical reliability, very important, because when we deal with prosthesis, even more for jawbone prosthesis, you can expect something very bad when you have a brittle fracture. So that's why we have chosen stereolithography, which is a technique that permits to make complex shapes with high accuracy. I'm going to explain you why by showing you how it works. So why can I make high accuracy parts? Because I work layer by layer by adding 25 micrometer thick layers and by making patterns of a specific shape for each layer. And when I add all these layers together, I have a polymerized product. So here, normally I can show you the video. Okay. Like that. So there is a syringe. In it, you have a ceramic paste. It's made half of ceramic and also of other components like a monomer. So I spread the paste, and then the scraper permits to ensure that the layer is very thin as we wanted and very regular, very flat. And then, as you could see, the laser is very fast and polymerizes the pattern I want on this layer. And I do it again and do it again. So the organic parts I have only stands to make the good shape I want, because after that, I will clean my parts, so remove the unpolymerized paste. And after that, I will put it in an oven for debinding, so removing all the organic parts, and then a sintering oven at very high temperature to densify and get very dense parts, ceramic parts. So I talked about the ceramic paste. You can see how it behaves here, but you also need to know what is in this paste. So the powder is the ceramic powder. It makes half of the volume, as I said, and it's very thin particles in order to have small grains and good mechanical performances. I also have monomers. Here it is a multifunctional acrylates mix. So I have a different functionality in order to get a great mechanical strength with not too much constraints, but in order to make it stand before the binding. I also need photoinitiators that are sensitive to the UV rays I send them, so they can initiate polymerization. Then I also have dispersants functionalized on my particles in order to repel the other particles and get a homogeneous paste. And I also have plasticizers that have different effects on the rheology of my paste, but they also permit to remove the constraints and avoid the formation of cracks even more during the binding. So this is roughly what is in my paste. And now to explain you where I am in this project, I'm currently studying commercial stereolithography, so SLA paste. And I do that to understand the structure of the paste and its properties in order to understand also its printability and how will I formulate my own paste. So the next step, I'm near this step now. So I will make several formulations in order to optimize the rheology for printing and to improve the interactions with the machine. And after that, when I will have the good paste, I will try to print the complex shapes of the biomedical implants I want to develop. So it involves challenges, SLA, which is the first challenge I want to discuss is mechanical performances. So I need great mechanical performances, and for that, we thought with my supervisors of ceria-doped zirconia. So it's a material which is a ceramic, which has been very much studied at MATEIS laboratory because it has a specific property, which is stress-induced transformation. And you see the term plasticity that might make you scream if you're a ceramist. But in fact, yeah, we can have a good toughness even if it's a ceramic and avoid brittle fracture, as you can see it on the strain stress curve, because the crystallographic structure changes when you apply too much stress, and you can see it here on the left. On the image, you have bands of transformation. So it's part of the material where the stress was maximal. And it released energy by transforming into monoclinic. So from tetragonal to monoclinic structure. And even more, you can get back your original material because you can make the transformation on the other way when you heat it a bit afterwards. So it's very interesting to print. And I told you that there exists commercial stereolithography paste, but not for this material. And we're going to understand together why. It's because of that. So here, my UV laser wavelength is in red. And you can see that at this wavelength, the commercial paste, which is in black, contains pre-white TZP, so it's a zirconia more well known that is not very absorbent. So here you can see the difference with cerium zirconia because of ceria-doped zirconia, because of the addition of cerium. You have much more absorption, and I told you that we have 50% of the volume which is filled by the particles. So you can imagine how it works on polymerization. So it changes a lot how it behaves. And we have thought of techniques to avoid this absorption and the change of the polymerization, maybe by functionalization or by making core-share structures. So we will do that after on the powders. And to make you understand a bit more, I can show you the scheme of the cured paste volume. So you can expect a different shape, more big on the side of the laser beam and less depth when you have more diffraction and also more absorption. So you lose in resolution, as we lost here. You can see on the right when the shape is a bit different from something rough. You can see that we didn't manage to be very precise because of a gradient of polymerization. So it's small layers that are a bit polymerized, but so as they are polymerized as much that you can't remove them, but not so much. So you will have defects on this side and you won't have the shape you want. So we have to also work on the machine parameters, on the contour, lasing. As you can see here, when you lase, you make all the surface of the parts, and then it goes very fast, but you have a contour lasing. So by adapting its parameters, you can have a better surface. So I work on that actually now. And I want also to tell you a bit about the rheology work I have begun. Why is rheology of the paste important? Because to make sure I have a very regular surface before polymerization, when I have my scraper blade, I need a low viscosity. So it would fill every void and be very regular. I have calculated that we are at a big scraping shear rate, so it's low viscosity at high shear rate, but I also need high viscosity at rest. Actually, I need to be self-supporting. So I don't want, when I don't scrape, I don't want my paste to go to fall around. I want it to be regular, so I need this type of behavior that you have with the paste in the commerce. At the right, you see a flow curve where you have a big viscosity at low shear rate and low at high shear rate. But the problem is that you see it's not regular. We have small shear thickening bumps, and this is linked to the evolution of the structure of the paste when you shear it. So we will make some experiments at the ESRF, so making rheology experiments while we will make SACs, so small angle X-ray spectroscopy, to understand the size and the type of flux, so of particles, aggregates that could be involved in these phenomena and to avoid them. So this was about rheology, and the last part I want to discuss is about osseointegration. So we will try to make this part at the end when I will have a good ceramic parts, and we will work with in collaboration with Laboratoire with femtosecond laser texturation in order to promote cell attachment and proliferation at the surface. So we'll have to find optimization because we want the good mechanical strength, but we also want to have a less dense part and to make specific patterns to promote the adhesion and also the bone growth on the surface. So you can see on the right result that has been made with samples that have not been printed, but of the same type of ceramics that is used. So I want to thank Manutech-SLEIGHT for permitting me to collaborate with Laboratoire Hubert-Curien for funding a part of my project also. And I want to thank also 3D Fab for hosting the big stereolithography machine that I use. And I want to thank you also for staying until the end of the presentations.